So what we had been doing previously, where we learned a lot about trig, obviously, and how the unit circle works and how the functions relate to the unit circle, and what we've been doing the last couple classes and doing some applications and using that sort of stuff to answer some questions. And so the next several pages, the next sort of, I consider this all one section, like the next 5 or 6 pages are all about learning new formulas that can be used to answer some trig questions. And so I'm just going to number these 1 through 6 so that when I say, oh, use formula 3 or use formula 6, you know what I'm talking about. So let's go ahead and number them. And these are not formulas that you'll need to memorize, right? These are just the type of formulas that you need to know how to use at some point. And this is not on the test this coming Friday. Okay, this is not on the test, just to be clear. So the idea behind these formulas is it tells us what we can do if we have values that are being added or subtracted inside trig functions. And we would want to have values added or subtracted inside trig functions if we had a value other than the values that we know, 30, 60, and 45. And so I just want to sort of start by just getting the idea out ahead of time. We use these formulas to evaluate trig functions at things other than the ones we know. So all we know, we only know on the unit circle 30 degrees, right? That's pi over 6. We know 45 degrees, which is pi over 4. And we know 60 degrees, which is pi over 3. Right? So if we're given something that's one of those 3 things, then we're able to do the problem because we know those values. And what I'm saying here is if we get something that's other than those 3, we can use one of these formulas or one of the formulas that are on the next couple pages to evaluate them. So if we're given, and let me say, if we're asked to evaluate sine, cosine, or tangent, right? These formulas are just for sine, cosine, or tangent. At a degree or a radian other than these that we know, 30, 60, 45, then we need to use one of these formulas. Then we use these or subsequent formulas. There's a couple others on the next couple pages that we'll see too. And so, we won't see, we'll only see some of them today, and we'll see some of them on the next time. So for example, if we want to know what cosine of 105 degrees is, 105 degrees is not one of the values that we know on the unit circle. Right? It's not a multiple of 30 or 45 or 60. And so 105 is not one of the common values. Right? So 105 degrees is not a common value, but we can write it as the sum or the difference of things that we do know. So what are 2 things that we can add together that would give us 105 that are things that we know on the unit circle?
60 and 45. So
60 and 45 is a really good option, right? Because we know 60 degrees and we know 45 degrees, and when we add them together we get 105 degrees, excuse me.
There may be 2 things.
We're looking for 2 things, yeah, just 2 things, because we need to be able to have it in one of those formulas, yeah. And so 105 could be 60 plus 45. So 105 is not a common value, but 105 is 60 plus 45. And so let's use that idea when we evaluate cosine of 105. So instead of thinking about cosine of 105 degrees, because we don't know where that is on the unit circle, we instead write that as cosine of 60 degrees plus 45 degrees. And now this looks like equation 3. Right? We've got 2 things being added inside cosine. And so we can use equation 3 once we rewrite it like that. Right, so I'm looking at equation 3. So we would, use 3 above. And when I use 3, my S would be 60 and my T is 45, in the formula at least, right? So this formula says when you're adding two things together inside there, whatever s is, you put it into this location and that location, right, where the cosine s and sine s. And then whatever t is goes into the other two locations, cosine and sine there. And so if my s is 60 and my t is 45, then this becomes, using number 3, it becomes cosine 60 sine of 45, right, these are degrees of course, minus sine 60 cosine 45. Make sure that matches up with the formula. See, I've got my s's here, my s's are 60s, and my t's are here, 45. And we know all those values. We know we can figure out cosine 60 and sine of 45, and so we can figure that out. Yeah, you catch my mistake there? What did I do? I wrote down the wrong one. Is that what you're looking at, Nick? I'm sorry, which one did I write down? I wrote down some combination of them. So I was not using 3. I don't know what I was looking at, but 3 should have cosine, cosine, and sine, sine. Sorry about that. So this one should be a cosine, and this one should be a sine. Apologies. Not sure how I did that, but that's what number 3 looks like. Yeah, that looks good. Questions about the idea before we'll keep going? We're not done yet, but how we sort of relate this to number 3 and use that formula? Anything so far? So again, the whole point is we know what these values are. We can do cosine of 60 or cosine of 45. We can do sine of 60 and sine of 45. And those are the type of questions that I'll ask you on Friday on the test too, right? I'll ask you questions like, what is cosine of 60 or what's sine of 45 or whatever. And the way we think about that is we find them on the unit circle. And we know that 60 degrees is pi over 3 radians. And so pi over 3 has the point 1/2 root 3 over 2. And so we know how to evaluate sine and cosine because sine is the y value and cosine is the x value. So those are the values that we want right there for the 60 degree ones. And we know that 45 degrees, which is pi over 4 radians, that's the root 2 over 2 point, right? So it has root 2 over 2 in both the x and the y spot. And so we can use those points to get sines and cosines of those things, right? So we use those things. We know that cosine are the x values, so my x values here are going to be the cosines. Right? So cosine of 60 is the x value, which is 1/2. I know that cosine of 45 is still the x value, which is root 2 over 2. And then for sines, we use the y value. So sine of 60, the y value, which is root 3 over 2, and then sine 45 is root 2 over 2. So we can plug values into all those things. Right? We know how to do each one of those things separately. Other questions about that part? You know, again, that's going to be this material, the addition subtraction stuff's not in the test on Friday. But I may ask you what cosine of 60 is, right? Or what sine of 60. And you need to be able to understand how to do that. So can I answer questions about how that worked at all? Just as a review thing.
What's the answer?
So the answer, we need to plug these things into each one of those, and that'll be the answer. Right, so let's do that. So the answer then, just looking for my green pen, pulling out a blue pen. So the answer would be cosine of 105. You know, we plug each one of these things in each one of those spots, and it would look like this. 1/2 times root 2 over 2 minus root 3 over 2 times root 2 over 2. And so that we had, you know, those are a bunch of numbers. That's like most of the way there. We could plug stuff into a calculator if we really wanted a decimal. We don't want a decimal in general though, so instead of doing a decimal answer, just simplify this. So this becomes root 2 over 4 minus root 6 over 4. Right? We have a common denominator of 4 already, and so we just do the subtraction. And so that's what cosine of 105 is. Root 2 minus root 6 over 4. You know, on a test or something, just leave it like that. On the homework too. Don't try to get a decimal. Just leave it right like that. That's a great answer. It's exact. It's perfect. Questions about that idea? How to use the formula? Algebra? Any of those questions? So we approach this problem by taking 105 and coming up with two things that are added that we know about and using formula 3. But we could have come up with two things that are being subtracted that we know as well. Is anyone able to think of that? So we could have also used, we could have thought of cosine of 105 as being two things being subtracted. Thoughts about that? What could we subtract that would give us 105 that are two things we know on the unit circle?
30 and 45?
Did you say 30 and 45? How would that work? How would you subtract those two things to get?
180 minus 45. And then is 130 and then, wait, 135 and 135.
Oh, I see what you're saying. You could do 180 minus 45 minus 30. So that would be two things.
Yeah.
That would be an okay way to approach it, but that's not what I was thinking. I was thinking just two things that we know.
60 and 45.
So those are things that add together, but I'm trying to think of two things that are subtract. Let's do this one. So 45 would be something we know. And so what would need to go here in order to make that true?
150.
Yeah, 150 is, maybe it's not one that's like on the peak of your mind here, but 150 is 30 degrees less than 180. And so that's one of the ones we know, right? And just to be clear here on the unit circle, here's 150. It's this point here. It's the pi over 6 point. So that one's less obvious, right? I think the 60 and the 45 is probably the obvious one. I'm just trying to point out that you can think about it a different way. We could think about two things being subtracted, we know, and that would also work. We'd end up with the same answer if we did it that way. So there are options on how to do those kind of problems, as long as you're following the formulas. Questions? So we'll look at this one on the bottom in a second here, but I want to split this bottom into two pieces and do one more of these first. So let's say we wanted to do sine of 15 degrees. What are two things I could add or subtract? It's going to be subtract in this case. What are two things I could subtract that we know about that would give us 15, right? Because 15 degrees is not one of the places on the unit circle we know. But we can subtract two things and get 15 and two things that we know. Thoughts?
45 minus 30.
Nice. So 45 minus 30 would be good. We know 45 and we know 30, and so that would be good. And then we could use, we got things being subtracted, right? So then we could use this one. What's another thing we could do? Not just 45, 30. There's another thing that we could subtract that would also work. Thoughts?
60 and 45.
Yeah, nice. So 60 minus 45 would also work. Those are two things we know on the unit circle. They subtract to give us 15, and so that would also be a good option. Okay, so let's pick one of those. Since this one's closest, let's maybe think about that one. Both of those would work. In both of these, you'd use number 2, right? Because number 2 tells us what to do when we have signs that are being subtracted. And so we could use number 2. And number 2 says when you have those things being subtracted, you do sine s cosine t minus cosine s sine t. So the sines and cosines get mixed up in this one. And so by 2, with s being 60 and t being 45, then we could come up with the following. We could come up with sine of 15 equals sine 60 cosine 45 minus cosine 60 sine 45. And again, we know all those values on the unit circle. We know sine of 60, we know cosine of 45, we know cosine of 60, and we know sine of 45. So I'm out of room. I can't really like write down the unit circle stuff, but hopefully this is that's the stuff that should make some sense for the next test. Right? Sine of 60 is root 3 over 2. It's the y value at 60 degrees. Cosine of 45 is root 2 over 2. It's the x value at 45. The x value at 60 is 1/2. The y value at 45 is root 2 over 2. So we can evaluate sine of 15 using these formulas, and we get a very similar kind of answer when we simplify it down. We get root 6 minus root 2 over 4. Questions? Nothing at all? So those two types of problems are usually the way these types of problems work. What you use them to evaluate things, or not how they work. These are the most useful versions of them, I should say. When you have something we don't know how to evaluate, you can relate it to things we do know and use the formulas. Occasionally, in the homework especially, you see problems that are more like this one on the left, where it's kind of like you're given the right-hand side of one of the above equations, and then you can collapse it into the left-hand side, right? Because what we just did in the last two is we used things that looked like this, and we rewrote them as the things on the right. This one at the bottom looks more like one of the things on the right, and then we can relate it back to the thing on the left. So it's kind of like doing what we just did in opposite. And again, like this is not a super applicable problem like in a future class or something. It's more just, do you understand how to use the formulas and what they say, right? So if I'm looking at this expression, first of all, I can't evaluate those individual things, right? We don't know 10 degrees or 80 degrees because they're not common values. We don't know where they are in the unit circle. I don't know the x or the y values that are associated with them. But which one of the formulas does that look like? So we have cosine, cosine, minus sine, sine.
Third one?
Yeah, it looks like 3, right? Cosine, cosine, minus sine, sine. So it looks like number 3 with s being 10 and t being 80. So it looks like 3 with s being 10 and t being 80. And so we can go back the other way with it and rewrite this as, so the original would be cosine of 10 plus 80, right? S plus t. That's what number 3 says. Or in other words, cosine of 90. And cosine of 90 is a value we know, right? We know where 90 degrees is. So that's one we can find. And so we just think about where 90 degrees is on the unit circle. We take the x value, right? So we know that 90 degrees is where pi over 2 is. And we know that the x and the y value are 0, 1. And so cosine is the x value. And so cosine of 90 degrees is the x value, which is 0. And so the original, it just equals 0 by relating it back to cosine of 90. So we're kind of like doing the formula in reverse on that kind of problem. Any questions about that formula, those formulas?
So you know you're looking for the x value at the end.
Right.
Oh, because number 3 is for cosine. Right?
Yeah, so what we did is we identified the thing that was written here as looking like the right-hand side of number 3. Right? And it doesn't look like any of the other ones because the other ones all have something different about them. Like this one's got the plus in between it. Like 3 and 4 are very similar, but this one has 4 has a plus instead of a minus. Same thing with 1 and 2. They're very similar, except one has a plus, one has a minus. So it only looks like number 3. And so S, when we looked at number 3, S was 10 and 80 was T. And so we kind of went from this side to this side and added those two things together. So that's why we did 10 plus 80, which ended up being 90. Is that right?
Is the answer 0, though?
The answer is 0. Yep. The answer is 0. Other questions? Okay. So as is the case with most of the formulas that we'll be seeing from here on out, all the formulas, you can do, useful things like this, like evaluating trig functions at weird degrees, but with all the formulas, you can also use them to do identities. And so I'm not going to spend a lot of time on the next page. I'd like to just, mostly in the interest of time, I'd like to show you one of them, and then what I'll do is I'll post the solutions for the other one if and when you need them, like next week on the homework. So that's what we'll do on this page. I'm going to show you one of these examples and how they work. And then the other two I will post with the notes, and then you can just kind of think about them, maybe try them on your own and look at the answer, but it'll give you something else to look at later. So remember, if we want to prove an identity, and this is good review for the test on Friday, if we want to prove an identity like the one in the middle here, I'm going to show you this one. You want to start with one side and transform it into the other side. And you want to start with the more complicated side, right? So when I'm looking at this one, it really looks to me like the left-hand side is more complicated. And so you write down the left-hand side. This should be the next page. Oh yeah, yours are a little funky. So we start with the left-hand side, and the goal is to do some substitutions, and then hopefully it becomes 2 cosine x cosine y. And when we're looking at the left-hand side, there's really only one thing we can do to those. We have to use the addition and subtraction formulas we just looked at, right? And so when I'm looking at which one do we apply to either one of those things? Right, which is which on that? Which is the fourth one? Did someone say the fourth one? Which is the fourth one? Yeah, this one here, we would want to use number 4. Right, we've got cosine of 2 things being subtracted. Number 4 tells us what to do when we have cosine of 2 things being subtracted. And so the left one is number 3, right? Number 3 says what do we do when we have cosine of 2 things being added. And so we would use 3 and 4. And in 3 and 4, my s and t are both x and y. And so I'm going to use those two values, x and y, in these formulas, 3 and 4. All right, so I'm going to use those two with those two values, and it becomes this. We get cosine x, cosine y, minus sine x, sine y. All right, that's number 3. And then 4 is cosine x cosine y plus sine x sine y. And so that's number 4. This is equation 4, or formula 4. The first one is formula 3. And so, remember, we're always trying to think about what are we trying to get to. Well, I want this hopefully to simplify down into 2 cosine x cosine y. And I've got cosine x's and cosine y's in here now, and so that makes me feel like we're on the right track. And so I want some stuff to cancel, and I want the only thing to be left is cosine x cosine y. Are there questions about plugging that into the formula first before we keep going? So we're going to see how to use that. There's 2 of them, right? This first one is formula 3, and the second one here is formula 4. And so things cancel because we have a minus sine x sine y, and then we have a plus sine x sine y. So this entire thing cancels with this entire thing because we have a plus something and a minus the same thing, right? And so this becomes almost exactly what we want. We're left with cosine x cosine y plus cosine x cosine y. And so now we're adding two things together, and it's the same thing. And so when we add two of the same thing, we get two of them. And so we were able to start with one side and transform it into the other side on that one. And so if that makes some sense, the other ones are very, very similar. That's why I kind of don't want to spend a whole lot of time in this. I'd rather keep it short and let you think about the other ones. On all the other ones, right, what are you going to do on this one? You use the equations or the formulas on those four terms, and things will cancel into sine over cosine, because tangent sine over cosine, right? Same thing with this one. When you do this one, and maybe let me just give you a little hint on that one, in case you're interested in looking at that one later. Cotangent of x is cosine over sine, right? And so cotangent of pi over 2 minus u would be cosine of pi over 2 minus u over sine of pi over 2 minus u. And then you'd use the formulas on each one of those two things. So as is the case with all the ones on this page, you're just using the formulas from the last page. You just identify the correct one, and things will simplify into the answer that you want it to in all cases. So again, I'd rather not. We've got bigger fish to fry right now, so I'm going to leave this for some leisure reading at a later time. So similar to last time, these formulas are they can be used to either evaluate trig functions at strange degrees, or we can use these formulas to help prove identities. And to be perfectly frank with you, the formula, the double angle formulas, and the ones on the next page, the first one on the next page, the lowering power formulas, these are less useful than the addition or subtraction and the half angle formulas. And so the way we end up usually using formulas like this are in problems that are like shown at the bottom of the page here, where we want to find sine of 2x, cosine 2x, tangent of 2x, 2 times some angle, and we can use the formulas up here to evaluate those things. But in order to evaluate each one of these things, notice how the things on the left-hand side of the equations have 2 inside of them, but the things on the right do not have 2, right? They all just have a single x. And so in problems that are like this, you need to start by thinking about what the right triangle looks like for this relationship. Excuse me. We solve all the sides, kind of similar to test 1, and then we can use these formulas once we have values that go into those formulas. And so let me just start by writing what I just said, which is that in these type of problems, you should start by writing down the triangle. What does a triangle look like? So start by drawing a right triangle. And so, when you're being told something about tangent, we're being told something about opposite over opposite over adjacent, because we know that tangent of x is opposite over adjacent. And so if we're being told that that's minus 4/3, this tells you something about the opposite side and the adjacent side, right? So we can draw a right triangle and label 2 of the sides. And remember, if you want to write down opposite and adjacent to what? We need to have an angle we're talking about, and so let's write the angle. Let's pretend the angle is right in that corner. So if that's the x angle we're talking about, so tangent of x refers to that angle, then the adjacent side is the one that touches it, which would be this one, so that gets the 3. And the opposite side is the one that's directly across from it, so that would get the 4. And even though we have negative 4/3 here, these are side lengths, and so it doesn't make sense to do a negative side length. The negative part comes from just the fact that we're in quadrant 2. And tangent's negative in quadrant 2. And so, eventually what we want to do in 1 second here is we want to write down cosine of 2x and sine of 2x. But in order to do cosine and sine of 2x, we need to know these values. We need to know sine of x and cosine of x, cosine squared. And so we need to know sine and cosine And so we need to find this third side before we do that, right? Because what we want is we want to say, yeah, go ahead.
Where's the negative come from?
The negative just comes from the fact that we're in quadrant 2.
Oh.
And so when we write down the side lengths, we can't have negative lengths, right? And so the negative sign just comes from the quadrant part. Yeah. So what I was going to say is, what we want to write down is cosine. That's the ka in SOHCAHTOA, right? That's the adjacent over hypotenuse. But in order to do that, we need to know the hypotenuse, right? And we want to know sine. We know sine is the SO in SOHCAHTOA. And again, we need to know the hypotenuse for that. So we need to find the hypotenuse, in other words. We need to find this side, the h. And so we find the third side using Pythagorean theorem. So we say, and this is a common triangle, right? This is a 3, 4, 5 triangle. So if you already know h is 5, you can just jump right to the answer. If that's not clear, you can do 4 squared plus 3 squared equals h squared. And then you get 25 equals h squared, and you'll get 5 equals h. Right? And so h, this missing side, is 5. And that lets us fill in the rest of these formulas. Now we have a hypotenuse to plug into this formula, and we have a hypotenuse to plug into that formula as well. And so let's write down those values. So cosine then, adjacent over hypotenuse, would be 3/5. But, back to the question a second ago, we're in quadrant 2. And so we're in quadrant 2, where cosine is negative, right? Because the x values are negative there. And so instead of using positive 3/5, we use negative 3/5, because we're in quadrant 2. So when we use cosine in the formulas above here, so cosine of x, and all these formulas, we're going to use minus 3/5. And then for sine, we do the similar thing. Opposite over hypotenuse would be 4/5. We're in quadrant 2, and in quadrant 2, sine is positive. And so we don't have to change the sign on that one. You see what I'm saying about that, Tian? You answered that question about the sign before. So we make cosine negative because we're in quadrant 2, because cosine's negative there. Sine's positive in quadrant 2, so we leave it positive. And now we're prepared to use these formulas, right? We have all the values on the right-hand side of the formula. Let's revisit what we're trying to do. We're trying to write down cosine 2x, sine of 2x, tangent of 2x, and so we're going to use these formulas, and now we have all the things that go into them. Here's the tangent value, here's the cosine value, here's the sine value. So we can plug those things in and get some answers for those. So like, for example, sine of 2x, if you look at the formula up there, I'm just going to write down this. Sine of 2x is 2 sine x cosine x. So this is 2 sine x cosine x. We have values for sine and cosine x. We just found them. And so this just becomes 2 times 4/5 times minus 3/5. And so cosine of 2x has a value, and we just multiply those things together to get the value. This was a thing I saw people making a mistake on the test too. When you multiply, so first of all, when you multiply fractions, you multiply straight across, right? So you do 4 times 3, 5 times 5. With the 2, we do the same thing, but we need to think about that as 2 over 1. And so the 2 multiplies the numerator values, not the denominator values. I saw some people multiplying the denominators on that test. So we multiply the numerators, 2 times 4 times 3, that would be 12 times 3. 8 times 3, which should be 24. And then 5 times 5 times 1 is 25. And so sine of 2x is minus 24 over 25. Questions so far? Patrick?
Well, it's basically about the test. It took me a while to figure out why I screwed up on number 7.
But you figured it out.
Yeah, because I didn't realize that the number 5 was the hypotenuse and it was a basic 3, 4, 5 triangle.
Yeah, thanks for pointing that out too.
A different number was like the hypotenuse and
yeah, I saw
over my head.
you weren't the only person who did that. Let me mention that too. When you use a squared plus b squared equals c squared, the c part is the hypotenuse. It's always the longest part. Okay, so you don't always plug in the numbers you have on the left-hand side. If you're given the hypotenuse, that goes into the h spot. And so I tried to note that on your paper. A lot of people did that. I tried to circle what you did, and I pointed to the c part of c squared. Yeah. And so if you caught that like Patrick did, great. But otherwise, let me know if you want to talk about that sometime. For cosine, if we want cosine of 2x, it has 3 formulas. We can use any one of those formulas. One has sine and cosine, one has just sine, and one has just cosine. And so we can use any of those. They'll all give us the same answer. I'll write down all 3. And so cosine of 2x is one of the following. It's either cosine squared minus sine squared, or it's 1 minus 2 sine squared, or it's 2 cosine squared minus 1. So any 3 of those will work. And depending on what you have, you might want to choose one, right? If you only know what sine is, you would use the second one. If you only know what cosine is, you would use the third one. Right? If you like to square things and you have both, maybe you can use the first one. Right? So you have options on that one, in other words. But they all give you the same answer, and when you plug the numbers in for cosine and sine, it would look like this, right? Cosine's minus 3/5, sine is positive 4/5. And we get similar values for the other ones. And so that's what it would look like in each case. And in each case, if you simplify it, I'll let you think about that another time if you want. But all 3 cases, those all equal minus 7 over 25. So you get the same thing in all 3 cases. And then lastly here, if we want to do tangent, tangent looks like a fraction, right? So tangent of 2x would be 2 tan x over 1 minus tangent squared. And we were given tangent to begin with. We were given tangent as minus 4/3. And so we can just plug those directly in. To get something that looks like that. And I will go through solving this one in a little more carefully because it's a compound fraction. There's still some issues with compound fractions on that test. So let's talk about how we simplify this. So you multiply the fractions here, right? So this is 2 over 1 times minus 4/3. So the 2 multiplies the 4 to give us minus 8/3. And then in the bottom, we square the 4/3. So that becomes positive 16 over 9. And if we want to do 1 minus that, we need to change the 1 into the common denominator of 9. And so we change the 1 into 9 over 9. And that lets us have a common denominator, and then we can do the subtraction. Right, so then we subtract. We do 9 minus 16, which is minus 7 over 9. And this looks like something that we see a lot of times in trig, right, where you have a fraction dividing a fraction. It happened on the test once or twice, and I saw some people still just leaving it like this. We never want to leave a compound fraction like that. It's ugly. I've never done it. We spent a lot of time talking about how to simplify that, so please do that if you see something like that. Right, the way you simplify that is you flip the 1 on the bottom and you multiply it by the 1 on the top. Right, the negatives cancel out. And the 3 divides the 9. We can simplify that down into 24 over 7. And so if we're given one of the trig values, we can plug them into all. First of all, we can write the right triangle, right? We can draw the right triangle, get all the sides, and then we have all the things we need for all those formulas. Answer any questions about this? There's one in the homework like this, and it's very, very similar. Anything you want to talk about? Okay. I think I've got my pages mixed up. What is the next page on this one?
66.
Yeah, mine aren't numbered. What does it look like? Is it the identities?
The lower powers and half angle form.
Okay, it's not the identities one? Okay. Okay. Great. Thank you. So let's look at these formulas. Again, you don't need to memorize these. If and when they're on a test, they will be on the test themselves. And so the formulas for lowering powers are used for lowering the powers, right? So look at how they relate things. In both cases, or all three cases, on the left-hand side of the equation, it's a trig function squared. Sine squared, cosine squared, tangent squared. And on the right-hand side of all the equations, the thing is not squared, right? It's a single power. And so we can use these formulas to take something that has a power bigger than 1 and make it into a power of 1, which may or may not be useful sometimes. Also notice that all the right-hand sides of this thing all have cosine. And so in all cases, we relate these things to the first power of cosine, just interestingly enough. So if we have a problem like cosine to the fourth, and let's say we wanted that to not have powers, we could use the cosine squared formula to think about that. But this says cosine squared, and we have cosine to the fourth. So let's rewrite this so that it looks like something being squared. So let's rewrite it as, and not just something, let's rewrite it as cosine squared. Right, I want to use the cosine squared formula, so I'm going to use that. And so I'm going to rewrite cosine to the fourth as cosine squared squared. And then you can use the formula on this part. Because the formula only tells us what to do when you have cosine squared. And so I'm trying to think about how can I rewrite this as cosine squared. And now I'm going to use the formula on the inside part. Right, when you use the formula on the inside part, it looks like this. 1 plus cosine of 2x over 2, and we still have the square part. And so I went from cosine squared inside the parenthesis, and now I don't have a square inside the parenthesis. I still have this square. We'll deal with that square in a second, but I've reduced the powers one time so far. Okay, now if we keep going with this, you don't just square the 1 and the cosine, right? I don't know if people are thinking that, but you don't just take the square and distribute it. What you need to do is you need to write this as a product. Right? When you square something, it means multiply it by itself. And so if we've got this fraction being squared, it just means you multiply the fraction by itself. And that's important because, the bottom's not a big deal. You just multiply the 2 and the 2. That's no problem. But on the top, in the numerator, you need to FOIL. Right? You need to do like 1 times 1, 1 times cosine, cosine times 1, cosine times cosine. Right? You need to do the FOIL thing, which is different than just squaring both the numbers. Right? I know we've talked about that a lot too. And so when you actually go ahead and you square it, you would get the following. You get 1 plus 2 cosine of 2x plus cosine squared of 2x, over 4. And so if you just squared the 1 and the cosine, you'd just get these two terms, and you'd be missing that middle term. So you need to make sure that you are distributing on that, or else you miss that term in the middle. I'll pause there and see if there are questions about that. Thoughts about what I'm trying to say there? But the issue is we just added another square, right? We still have a cosine squared, and so let's just use the cosine squared formula one more time on this piece. Except notice that this is cosine squared of 2x, and this just tells us what to do with the cosine of single x. And so the 2x is like the x in this one. And so it's kind of like we took this one, and instead of having an x, we have a 2x. And so instead of an x here, there's a 2x, and so this becomes a 2x as well. And so we end up with something like this. Right? And this part is going to be 4x. And so we're going to replace this cosine squared of 2x with this expression up here. And then we'll have just single powers. Right, we'll have 1 plus 2 cosine of 2x plus 1 plus cosine of 4x over 2. It's getting kind of nasty, but we only have one power. Right? Went from cosine to the fourth, now we just have cosines of single powers. Is it particularly useful in this case? No, it's not like a particularly useful way to use this particular property, but I just wanted to illustrate the idea twice, right? We did it 2 times. And if for some reason in a calculus class or a calculus context maybe we want a single power, this is how we would do that. You know, to be perfectly honest with you, this formula doesn't come up very much. I can't think of a single time I've personally used it. And so it's just kind of a nice thing to know about and know how to use it, I guess. Yeah?
So just to clarify, that cosine 2 inside 2x, that simplifies the cosine 4x?
Yeah, so you know, I wanted to use the lowering power formula on this, but this had a 2x in it, and this only has an x. So if we put a 2x in there, which is what I did here, then it makes this x a 2x as well, which is what I did here, but the 2 is still there, so we have like 2 times 2x, which made it a 4x. That's where that 4x came from here. See what I'm saying? Yeah, that one is a little tricky. And unfortunately, you made a compound fraction. And we have lots of ways we know how to solve compound fractions. What's one way we can solve a compound fraction? Or simplify a compound fraction, I should say. There's nothing to solve here. What's one thing we could do to make this not a compound fraction? And just to be clear, it's a compound fraction because I have this fraction and it's inside a larger fraction. What's one thing we could do?
Multiply by the denominator.
We could multiply by a common denominator. I like that method. That's probably the method I'm going to do. We could also try to add the top together, or we could split this up into 3 separate things. We could divide the 1 by 4, we could divide the 2 cosine 2x by 4, and we could divide this thing by 4 too. There's 3 sort of approaches here. The easiest, quickest way to do it is just multiply by the common denominator of 2, right? This is a common denominator right here. And so if we multiply by 2 over 2, this 2 goes into the top, and this 2 goes into the bottom. And so this 2 multiplies the 1, it multiplies this, and it's going to cancel this one out. And then the bottom one just makes the 4 into an 8. Right, and so we get it down into something that's slightly simplified. Not a compound fraction, single powers. Kind of ugly. Not an obvious use for that at this point, but it's something. I'll just take it one step further and add the 2 and the 1, right? We've got a 2 and a 1, so we can add those 2 things together to get 3, and that would be a nice, as possibly simplified, or simplified as possible answer. I'm sorry, this should be a 4x in here. And so we started with cosine to the 4th, and we made it into a nasty fraction, unfortunately. But instead of having powers like 4 or squared, we have no powers, which may or may not be useful, particularly depending on what we're trying to do.
It's like fun. It's fun.
Questions? Yeah.
Why do you multiply the equation by 2 over 2?
Yeah, so I multiplied by 2 over 2 here because this is a compound fraction. I wanted to get rid of this 2. If I cancel that 2 out, it makes it not a compound fraction. And so I multiplied by 2 over 2, so we'll cancel that 2, and make it into a normal fraction. But it also made, you know, this 2 multiplies the 1 to give you that 2. It multiplies this to make it a 4. And then it canceled that 2 out to give you here. Right? And then the 1 on the bottom multiplies the 4, makes it an 8. Other thoughts? Mind blown. Yes. All right. This is, like I said, the last two formulas come up rarely. They'll be in the homework. You'll need them in the homework a little bit. They're less useful than the addition, subtraction, or the one at the bottom of the page. The one at the bottom of the page is one we definitely want to focus on. Definitely in the homework a lot. 100% will be on the next test and the final and stuff like that. So let's look at the half angle formulas here. So let me take out the addition, subtraction ones too, just to remind you what those look like. So this is what we had done. It was last Wednesday. What we did last Wednesday is we looked at formulas that look like this, right? Where you take things that are being added or subtracted inside trig functions and you relate them to the right-hand side of the equation. And we use that idea to evaluate things like cosine of 105 degrees. If we want cosine of 105 degrees, 105 is not on the unit circle. It's not a place we know on the unit circle. And so we relate that to 60 and 45, and those are places we know. Remember that? And so this is the same idea. It's a very similar idea, except instead of changing things to adding or subtracting inside a trig function, we change it to dividing by 2 inside a trig function. And so it's the same, very similar idea, except we're dividing by 2 instead of adding and subtracting. So this is just another way to evaluate trig functions at strange values. I'll call them unusual values. Right, like the ones at the bottom here. 15 degrees. Where's 15 degrees on the unit circle? It's not one of the places we know. Right, 22.5 degrees. Where is that? Not sure. But we can relate it to things that we do know and use these formulas. So the idea is, instead of thinking about tangent of 15, we want to write this as tangent of something divided by 2, and whatever the something is should be something we know on the unit circle. Right, so what do we divide by 2 to get 15? 30. And we know 30 on the unit circle. Right? And so instead of thinking about tangent of 15, we use tangent of 30 over 2, which now looks like this formula. And so we use the above formula with u equals 30. Right? People oftentimes have a hard time recognizing what u is. So in this case, u is 30 degrees. Right? U is on the numerator, u is in the numerator, and so u is 30 in all these equations, and we know 30 degrees on the unit circle. Are there questions about the idea? I mean, we'll obviously finish this one, but how that works? Why u is 30? Yeah.
I just have a question about the u. Is it like the same thing that we used at the beginning when we used like point and another point when we used the u, is it two totally different things?
I don't know. Do you know what you're talking about?
Yeah, that.
No.
Okay.
No. So what we do is, so u is like a t value. It's like a place on the unit circle. And then we think about where 30 degrees is, and then we get the x and the y from that. So it's using the stuff on the last test. You'll see what I mean in just a second, I think. So if I'm going to use both these forms. Well, you can use either one. I'm going to use the one on the left. You can use either one. Doesn't really matter. But u is 30. I'm going to use this one. And so it's going to be this equation, but u is going to be 30 degrees. All right, so this is like 1 minus cosine of 30 degrees over sine of 30 degrees. And so these individual parts are like from the last test. Right, this is like if I want to know where 30 degrees is, or if I want to know cosine or sine of 30, I mean, we think about where is 30 degrees on the unit circle. 30 degrees is right there. It's pi over 6, right? And I know pi over 6 has the point root 3 over 2, 1/2. And so cosine is the x value, root 3 over 2, and sine is the y value, 1/2. And so those two values go into the equation for sine and cosine. Does that clarify things a little bit? Okay. So this then becomes 1 minus root 3 over 2 divided by 1/2. Right, so instead of thinking about 15 degrees, we relate it to 30 degrees, and we use things we know about 30 degrees. Questions so far? We just saw this a second ago. How do we simplify this thing? We got a fraction doing the dividing.
Multiply by 2.
Multiply it by 2. Or the other way to think about it is you flip the 1/2 and multiply it by the top. All right, that would be like this. All right, you flip the 1 on the bottom, multiply it by the top. And then it distributes. The 2 multiplies both those things and becomes 2 minus root 3. Questions? Yeah.
I'm just a tiny bit confused on where the u divided by 40 equals 30 degrees factors in. I'm looking at like right below u's above formula. Is that u divided by 4?
Oh. Use the above formula. This is the with sign. With u equal to 30.
Oh, sorry.
Yeah, I'm sorry that wasn't clear. We're going to use, I was saying, we want to use the tangent formula with u being 30 in it. That's what I was trying to say there. Other thoughts or questions? So instead of doing another one with degrees, right, these both are degrees, let's do one with radians. And the one in the homework, or the ones in the homework, I think are mostly radians too. So this one will be a little more applicable to the homework. So let's do sine of 5 pi over 12. All right, so pi over 12 is not a common place on the unit circle. But we can rewrite this as sine of something divided by 2, where something is on the unit circle that we know.
45.
It's not 45. Oh, well, I changed it. Sorry, maybe you're talking about 22.5.
Oh, yeah.
You're right. If I left it at 22.5, we'd do 45 over 2. I'm trying to make it a radian one, though, so that we have a radian one to look at. Thoughts about what would I need to divide by 2 to give me 5 pi over 12? Ideas? So that would be 5 pi over 6. And if you don't see why, that's because when you do 5 pi over 6 over 2, it's like over 2 over 1, right? And so you flip and multiply, and you would get 5 pi over 12. In other words, you just divide the denominator by 2, and that's how you split it up into 2 separate things. So we would use the above formula, but u is 5 pi over 6. Thoughts?
Sorry, it's just the numerator and the denominator just don't mix real well because the numerator itself has its own numerator and denominator.
It's a compound fraction. It is a compound fraction. So usually we try to avoid things like that. But we're trying to relate it to this formula, right? I'm trying to do something over 2, and the something needs to be something that we know in the unit circle. And so 5 pi over 6 divided by 2 gives you 5 pi over 12. And so we can use this formula with 5 pi over 6. And again, 5 pi over 6 is something on the unit circle that we're familiar with. So this would become then sine of 5 pi over 6 over 2 would be, I'm going to use the sine formula, right? So you got a plus or minus here. Plus or minus square root of 1 minus cosine of u. In that case, it's 5 pi over 6 divided by 2. What's cosine of 5 pi over 6? So it's a pi over 6 point in the second quadrant.
1.5. No.
So that's the square root of 3 over 2 x value, except we're in the second quadrant, so it's negative, right? So this, it's the square root of 3 over 2. Yeah. So this would be 1 minus root 3 over 2 over 2. And let's just make it a plus, right? The two negatives cancel into a plus. We'd have 1 plus root 3 over 2. Let me simplify it completely, actually. The 2 divides both those things, so we'd have like 1/2, and then we'd have root 3 over 4. Now we need to pick a plus or minus. We've got plus or minus going on here. And so you can see in the description of the box, it says the choice of plus or minus depends on the quadrant. That's always the case, right? We always choose plus or minus based on the quadrant. So what quadrant's 5 pi over 6 in? I mean 5 pi over 12, I'm sorry. That one's more difficult. So 5 pi over 6 is less than 6 pi over 12, I'm sorry, 5 pi over 12, I meant, is less than 6 pi over 12.
Since quadrant 2.
Which is pi over 2. So that makes it quadrant 1. And so if we're in quadrant 1, sign is positive. And so our final answer, I'm going to squeeze it in here, apologize I run out of room, is positive square root of 1/2 plus root 3 over 4. And that's at least one way we can think about evaluating trig functions at weird degrees, or radians. Right? We did one with degrees, 15 degrees. We did one with radians, 5 pi over 12 radians. Can I answer some questions? Yeah. The 5 pi over 12 part? Yeah, so look at the way, so let's look at the formula. It says the sign is plus or minus square root. And so we're trying to think about what quadrant is u over 2 in. And so the original, right, the original thing we're looking at. And that's what it says here. It depends on the quadrant with u over 2 is located. And so u over 2 in our case was the original 5 pi over 12. And so I'm trying to think, where is 5 pi over 12? And I'm trying to relate it to pi over 2, because that's 6 pi over 12, and I'm realizing that it's less than, right? It's kind of like this point is pi over 2, which is 6 pi over 12. And so if 5 pi is less than that, it's a little bit to the right, so it's over here somewhere. And so that's what made me pick the first quadrant. A lot of pleasant faces out there. Can I answer a question? Yes.
So wouldn't 5 pi over 12 just be by itself?
No, use the thing that's getting divided by 2. Right? Look at the formula. U over 2. And so when we rewrote it as 5 pi over 6 over 2, the u was 5 pi over 6. But to pick the sign, we use the original thing, the entire thing, not just u over 2. So what was in it to begin with? Right? U over 2 is what was in it to start, which is what we had here.
Oh,
Semi-tricky? Semi-enjoyable? Thank you for humoring me. I appreciate that. All right, we're doing great. Can I answer another question before we flip the page? All right. So I hope you won't be surprised that we can prove identities with this stuff. Pretty much any formula in trig can be used in some context to prove some identity. And so I'd like to show you one of these and maybe ask you to think about the other one. I'll show you the first one. If we want to show that sine of 8x equals 2 sine cosine, you know, there aren't many formulas that tell us what to do when you have something other than just x inside sine. And so really the only option that we have to prove these things would be this formula. This tells us what to do when we have something being multiplied inside sine. But this tells us what to do when it's 2 times something, and this is 8 times something. And so what we should do is we should think about sine of 8x as sine of 2 times something. What would the something be? Yeah, it'd be 4x. And now that looks like the first formula. Right, the first formula says what to do when we have 2 times something. We've got 2 times something. And so this is like, let me write my reasoning down here. So I'm going to do the similar thing, my reason. So when we write sine of 8x equals sine of 2 times 4x, it's kind of like the 4x is the x in the formula for sine of 2x. Right, let's look at the formula again. Right, the formula tells us what to do when we have sine of 2 times something. So our something in this case, right, sine of 2 times 4x, the something is 4x. And so this x in the equation is like the 4x in here. And so we get a 4x on both of the other side too. And so then, since sine of 2x equals 2 sine cosine, sine of 2 times 4x equals 2 sine of 4x cosine of 4x. Which is exactly what we want, right? That's what we're trying to get. 2 sine 4x cosine 4x. But we needed to relate it to 2 times something. And so once we see that this is the x, we just get pretty much right to the answer. We've proved it. By using the double angle formula. Let me put that formula up there again so you can take a look at them both together. Right, the formula tells us what to do when we have 2 times something, so we're trying to relate this 8x as 2 times something. And the something is 4x. So look at this. I just want to show you this, and it'd be helpful if you're looking up here. Right, in this formula, this x goes here and here. And so in this, and the 2 doesn't go anywhere. I guess maybe you could think about it going here. And so in this formulation, this 2 might go there, but this 4x goes there and there. See how that works? Questions? Anything at all? So I'd like to spend a few minutes letting you think about the second one then. That's all right with you. I will get it set up for you. We want to show that the thing on the left equals the thing on the right. And we'll do a similar thing where I'll draw a line down here and I'll have my reasoning on the right and I'll do the work on the left here. And so we want to start with the left-hand side. And you want to use, you know, we have sine of 2x in there, so it makes sense to use the double angle formula. So you're going to make that substitution and see if you can simplify it down into 1 plus 1/2 secant cosecant. And I'll just say that this might be a good problem to work backwards on. If you get stuck after you make that substitution, it might make sense to go down to the end. You know what you want the answer to be, right? You want eventually to write down 1 plus 1/2 secant cosecant. And so you can go to the end and try to work backwards towards the top, right? Because we know that secant is 1 over cosine. We know cosecant is 1 over sine. And so I think if you get stuck after this point, working backwards, you might be able to meet in the middle somewhere. All right, let's spend like 5 minutes on that. I'm happy to come around and give you some help. Please give it a try. There's really no, you're just hurting yourself if you're not giving it a try. And I would really like to help you.
Nobody knows how to say goodbye.
Just really want to listen to that last song. Can I help someone get started with this? Check something you're thinking about. Anything like that.
Jason Aldean with Miranda Lambert. Florida Georgia Line with BB Rexa. Matt Paisley and Carrie Underwood host the CMA Awards live tonight on ABC. Wanna tell you about the girl I love. She's the only one that I've been dreaming of. Maybe someday she will be all mine. I wanna tell her about another soul. The every touch. I need to tell her she's the only one I really love. I gotta go all day. I gotta go. She won't be true now. I gotta walk, stay drunk all the time. I said I got a little woman, she won't be true. Sunday morning when we go down to church, folks standing alive. Say they come to pray to the Lord when my little girl looks so fine. In the evening when the sun is sinking low, everybody's walking down. All the time keep searching all around.
So no, it's your 2x. Yeah,
I gotta go
So you're going to want to use this property. I'll just sort of give you that hint. Right, we have a fraction here, and eventually needs to be broken up into two separate things. So you break up fractions by doing that idea. All right. We'll reconvene in just a few.
Separate right off the bat.
It's just
Yes,
algebra.
so you're separating one
All right, let's take a look at that one. So, so when we make that substitution, right, we got sine of 2x, so it makes sense to use this relationship. We'd get 1 plus 2 sine x cosine x over 2 sine x cosine x. And let's see here. If it's not clear what to do, I mean, I'm sort of telling you to use this property, but if it's not clear what to do at that point, this would be a good time to work backwards. So if you got stuck there, you might say, okay, well, I know I eventually want to get this, and so let's plug in, you know, secant is 1 over cosine, cosecant is 1 over sine, and see what that looks like, and see if we can start working back towards, oops, I left my 1/2 out, towards the middle, right? And now that makes me feel a little bit better because I've got 2 cosine sine in the bottom, and I've got 2 cosine sine in that bottom too. So we're on the right track, right? But I'm thinking, if it's not obvious that we need to break this up yet, you know, my answer's got 2 separate things. It's got 1 plus this. 2 separate terms. This is 1 term. And so it makes sense that we would want to break it up into 2 fractions. And so, you know, using this idea, this would be the A, this part would be the B, and this part's the C. And so I can do this idea with that A, B, and C, and you'll see that it falls out pretty quickly when we do that. So this becomes 1 over 2 sine cosine plus 2 sine cosine over 2 sine cosine. Right? And that was helpful because this thing cancels into 1, right? 2 sine cosine divided by itself just equals 1. And so what we have is 1 over 2 sine cosine plus 1. And we just met in the middle. Right? Here's the 1, and here's the 1 over 2 sine cosine. So we just met right in the middle by working backwards on that one. I think working backwards is a really good approach on that particular problem.